Good afternoon, everyone. First thing we're going to do is quickly finish summarizing the lab activity from yesterday. So if you don't already have that out, please get out that handout and we'll briefly talk about what's going on here. Okay, so the first one was all these shapes from these graphs. So how it goes in both rows, right, it's horizontal line, okay, slant, kind of like y equals x. Okay, when you zoom this one out, it's parabola. And for the last one, it should look cubic. Okay, and it's same for the row below. They do the same thing. To answer the question, how does the degree of the numerator and the denominator affect the appearance? So basically, when you compare them, right, or subtract, take the difference between your powers here, which is basically following the exponent law. Right? If I do x cubed divided by x squared, that's x to the 1, and that's linear. Okay, so the difference in the powers is the shape. Okay, so yeah, just taking the difference between those picture powers, right? 5 take away 2, it's 3. So it looks cubic. It looks like x to the power of 3, right? We know again it zoomed in and has asymptotes in the center, so it's not exactly the same, but in the big picture, that's kind of what it looks like. Okay, for the bottom half, hopefully what you noticed when you ran these through, all of these graphs, when you draw them, so some of them they might look like this. Okay, some of them may have looked like this. Okay, but in both cases, the dividend, when you added it on, should look like an asymptote kind of running between those, but it's on an angle. Okay, so the key thing to take away from this one is that the asymptote, or the dividend, is a slant asymptote. Okay, and this is something new, right? That you may not have seen before. That it's still approaching a line, but the line happens to be on an angle. And actually, technically, what's happening in those previous examples, when it looks like a parabola or looks like a cubic function, is essentially the same idea, right? It is approaching an asymptote that is made up of a higher degree function, right? A parabolic asymptote or a cubic asymptote, and so on. Okay, so that's the basis of today's lesson. So now that we know all these things about these functions, we're going to put it to work and work on curve sketching some of these functions. Okay. So here's the summary from yesterday. Okay, and I know on the page we did like, D over C and A over C, things like that. But in the summary, you're going to try to leave this a little more general. Okay. So the vertical asymptotes of the function are always the roots from the denominator. That turned out to be the D over C on your handout. But that's what it is, right? Vertical asymptotes come from the roots of the denominator. Okay, the horizontal asymptotes are the ratio of the coefficients of x. Now, this is only true because they were the same power, right? In all those equations on the first page, you had, like, if you had 3x over 2x, then the horizontal asymptote is 3 over 2. Okay, but it only works because it's both just x. There were no, x squared over x or x cubed over x or something like that. Okay, the x-intercepts, okay, and again, in the handout, we said that was b over a, but that's basically the roots from the numerator. Right? If you solve the little expression in the numerator, that's where your x-intercepts occur. Okay, and the y-intercept is the ratio of the constant terms. So that was b over d in that handout. But yeah, the key thing is it's the constants from the numerator and the denominator. Okay, so the only one that might need a little explanation here, I think, y-intercept, you plug in y equals 0, so that's why it becomes b over d. The horizontal asymptote may need a little bit of explaining here, so I'm going to show you a couple ways. Okay, so we're going to do this algebraically. Now for this one, for the first explanation, you don't have to copy this down. Okay, I just want you to watch and see what happens here. So the expression ax minus b over cx minus d, well, that's really division. So we'll try a four-star division here. So what do I have to multiply cx by to get ax? Well, I have to multiply cx by the fraction a over c. Okay, that would give me, right, the c would then turn into an a. Okay, so I'll multiply that out. So I would have my ax. Okay, ac times d, that's minus a d c. Okay, and then b take away that. So we really have negative b plus ad over c. Okay, and I'm already done. Like there's no x there at all. Okay. So if I write out my division statement, you may recall one of the division statements would be just to write the original. So ax minus b over cx minus d would be equal to this part. So a over c. We have a negative here. So minus, this is going to look really messy for a second, b plus ad over c, and that's all over the other part, cx minus d. Okay, so that might not look like we've helped much, although I did separate the AC from the rest of it. Okay. So the horizontal asymptote is related to the end behavior. So as x, so it would be this number right apart right here. Okay, as x goes to infinity, so x gets very, very, very large. Okay, what happens to this second block on the outside? Okay, well, if x gets very large, then my denominator is going to be very, very large. Okay, and the top, which is all constants from the original equation, that's not going to change at all. So you have a number being divided by an increasingly huge number. So this part, right, that I highlighted in yellow, that's going to tend to 0 as x gets really, really big, and therefore disappear. Okay, so that's why a over c is our horizontal asymptote. Okay. We're going to do another explanation that's going to talk about this idea of really, really big in a moment here. But first, to do that, we need to talk a little bit about infinity and how to manipulate it in an equation. Okay, so again, I don't know if you've ever seen any of these before. But I'm going to kind of zip through them here. Okay, starting with the left-hand column. Okay, if I have infinity equals infinity, so the idea that, incredibly huge numbers plus incredibly huge number, okay, that's still infinity. It's just very, very big. Okay, same goes for infinity times infinity. Right, something incredibly huge number, vast number times another one is still a vastly huge number. Okay, next two are a little weird. Okay, subtracting and dividing infinity over infinity are what we both call indeterminate forms. Okay, and the reason for that is even though it has the same symbol there twice, right? Infinity minus infinity. It's not necessarily true that they're the exact same size. Okay, so I don't really know what's going on there. Same with the dividing. It's hard to compare them that way. Okay. On the flip side, okay, if I have infinity and I add some quantity to it, well, it's still infinity. Okay. If I have infinity and I subtract something, well, it's still infinity. It's just still a really big number. If I multiply by a constant, it's still infinity. If I divide it by a constant, it's still infinity. Okay, last but not least, if I have a constant divided by infinity, right? So that's like that last example we just talked about. If I had even if k was large, like 15 million, infinity goes on forever. So as we tend to infinity and it gets bigger and bigger and bigger, this is going to tend to 0. Okay, so that last little bit is what's going to inform our second algebraic explanation of that asymptote. And yeah, this one you might want to take down because it's probably the more useful of the two. Right? If we want to check the end behavior, so what happens at infinity, well, we'll just plug in infinity and see what happens using the rules we just had. So I have, for f of infinity in this case, I would have a of infinity okay, minus b over c of infinity minus d. Okay, from our rules, a is a constant, and so is b. So a times infinity is infinity. Take away b is still infinity. Same with the denominator, infinity over infinity. Okay, it's indeterminate. Okay, doesn't work. So the trick we're going to use is at the very beginning, I'm going to take my rational function and I'm going to divide everything by x. So I had ax, now it's over x, minus b over x, cx over x, minus d over x. Okay, so when I tie this up, I get a minus b over x and c minus d over x. So now, once again, we sub an infinity. So a minus b over infinity, c minus d over infinity. Okay, but from the properties we just talked about, okay, b over infinity, apologize, it doesn't really look like infinity. B over infinity and d over infinity, those two pieces right there. Okay, well, they are going to tend to 0, right? A constant divided by infinity is 0, and that leaves me with a over c. And that's why it follows that asymptote the way it does. Okay, so finally, we're going to put this all together to do sketching of some graphs here. So f of x, 3x minus 2 over x, 5 minus x. Okay, so if we want to use the shortcuts from yesterday, the first thing we should note is that our denominator is reversed. So I have 3x minus 2 or negative x plus 5. Okay, and now if you want to, we can just apply those shortcuts we used yesterday, right? So we'll start with the vertical asymptote. Okay, my vertical asymptote is going to be 5. Okay, so we'll add this onto our graph as we go. 5. Okay, my horizontal asymptote. Okay, that's the ratio of the x terms, so that would be negative 3. So I should have an asymptote down here. Okay, my x-intercepts, my y-intercepts. Okay, my x-intercept is the root from the numerator, which is 2/3. Okay, and the y-intercept is from the denominator, so that's 5. Okay, so we have y-intercept of 5. Okay, x-intercept is 2/3. Okay, so that must be my graph looks something like this. This part goes up and heads over towards the line, and this part is down in the bottom. Okay, so continuing on. Okay, next thing, and again, this is kind of on your sheet, right? The degree of the numerator and the denominator influence the shape and behavior of a rational function. Okay, this is going into a little bit more detail. Okay, right, if the degree of the numerator is 1 greater than the denominator, then the function tends to align. Okay, that idea of a slant. The specific name for this is called an oblique asymptote. So now we have vertical asymptotes, horizontal asymptotes, and oblique asymptotes. If the degree of the numerator is 2 greater than the denominator, right, so the difference of the powers is 2, then it would tend to a parabola. Okay, and of course, more generally, that means the degree of separation between the numerator and the denominator tells you what the end shape would be. Okay, so if the numerator was like x to the 7 and the denominator was x cubed, the difference between those powers is 4, so it would be a quartic function. So it would tend towards a quartic function. Okay, last but not least, the equations of these non-horizontal things, okay, can be obtained by just doing division, right? You divide, okay, and the dividend that you get, that is the equation of the asymptote that it tends towards. Okay, so let's try it out. Now we're going to sketch the graph of x squared minus 5x plus 6 over x minus 4. Okay, so we'll start with our vertical asymptote. Okay, so again, generally speaking, right, we said that's the roots from the denominator. So we would have it at 4. Okay, now horizontal asymptote. Okay, that does not exist here. I should say NA there. Okay, because the degree of the numerator is 1 more than the denominator, it tends to an oblique asymptote. It's going to tend to the linear function. So for the oblique asymptote, this is where we do that quick little bit of dividing. Okay, so I have x minus 4 going into x squared minus 5x plus 6. Okay, so we have x okay, I don't even really have to finish this. Remainder is 2. Okay, but there's the key thing. So my oblique asymptote is x minus 1. Okay, for the x-intercepts, okay, the x-intercepts are the roots of the numerator. So if I pop back up to my original function, let's factor the numerator. So that is x minus 2 and x minus 3. Okay, so that means I'm going to have roots at positive 2 of the 3. Okay, my y-intercept And we know that the ratio of the constants. So the constants are 6 and negative 4. So my y-intercept must be negative 3/2. Okay, so with all that information that I have there, we are now ready to create our graph. We have vertical intercept of 4. Or sorry, vertical asymptote. Okay, we don't have a horizontal asymptote. The oblique asymptote is x minus 1. So as a quick review, right, that means my slope is 1, my y-intercept is negative 1. So my oblique asymptote is something like this. Okay, my roots are 2 and 3. Okay, and my y-intercept was negative 3/2 or negative 1.5, right about there. Okay, so this is enough information to kind of piece together what's going on. Okay, we could do testing around our asymptote to see which direction it's going, but I think we probably have the idea here. In the bottom, okay, it's all underneath the slant asymptote, so it must be kind of sandwiched where it goes close to this asymptote and close to that one. So that's my one piece. Okay, on the other side, we might be wondering, well, where should it go? Right? Should it go down here or should it go up here? Okay, and the clue is, if it was to go on the bottom half of that, there would have to be another root somewhere because it would have to cross over this axis. Okay, so it can't be on the bottom, so it must squeeze into that piece on the top. So my other piece of the graph looks like that. Okay, so again, with those key features, right, the asymptotes and the intercepts, that allows you to get a quick sketch of what the graph would look like. Okay. All right. Last thing from the note from yesterday, or from the activity from yesterday. Okay, and again, this is kind of a new thing. If you went through and factor, you would have noticed, right, you only get a remainder of 0. Okay, which means that actually the denominator was a factor of the numerator, and it would divide out or cancel out evenly. Okay. So when that happens, we don't have the asymptote anymore. Okay, but because technically we're not defined where the asymptote would have been, we have a hole in the graph, which is something new. Okay, so for example, we're going to do a quick sketch of x squared minus 3x minus 10 over x plus 2. So same idea. If I factor this, okay, I'm going to have, let's see, well, negative 10. So it's going to be x plus 2 and x minus 5 over x plus 2. Okay. So before I go ahead and cancel, I note, right, my restriction is that x cannot equal negative 2, because that's where my vertical asymptote would be. Okay, but these two things cancel out. So this function really looks like x minus 5. Okay, so what looked like a rational expression, you know, for the most part, is just that line, x minus 5. Okay, so I'm going to draw that line, okay, but the only exception is that I have a hole. Okay, right? It says x cannot be negative 2. Okay, even though I've dealt with this, right, originally, I can't have a value at negative 2. So when I graph this, all I have to do is at the x coordinate for negative 2, we just draw that it has a hole. So it was x minus 5, I believe. Okay, so that means I have negative 5. Apologize, my line needs to be ironed. But basically at negative 2 with a hole, we just draw a hole to say that there's a gap in the graph there. Okay, and everything else is fine. And what's actually really interesting about this, just bear with me for one final thing here. If you graph this function in Desmos, okay, you can see it looks like the line that we talked about. It's x minus 5. Now, you don't actually see a hole in here. And if you zoom in, you're never going to see a hole on the graph. Okay, you can't really zoom in enough. Well, maybe you probably can zoom in enough to break it a little bit. But if you tap on the graph, you can see you get a little point slider so I can see what is going on. Okay, so if I keep sliding this, let's see what happens when I hit -2. Oh, there it is. Okay, there's the hole. It briefly says undefined at that point. Okay, so that's how you can see it in Desmos. So you just use the point slider, and it's there. Okay, so that was pretty quick. But yeah, the key thing again for rational functions is you're going to use your intercepts and your asymptotes to get the sketch of the graph. Okay. So finally, to practice that, there's some practice questions that will allow you to practice sketching some of those interesting rational functions. Okay. There's a lot of stuff in there, but I appreciate your patience. Thanks for watching, and we'll see you tomorrow.